The core of an spectral domain OCT system is a spectrometer in the detection arm. In general, light is detected in the spectrometer, and this is usually achieved by CCD or the charge coupled device. So here we have a fiber, for example. We have a fiber here, and we are sending light in this direction. There is a grating here. It will split the light in different wavelength, and this lens will focus the light on the CCD camera, and we are detecting the light, and from there we are generating the image. But as we know that light is a photon. Actually, we are sending the light as a photon, and light is a particle. So there will be some issue. There will be some noise. So I will talk about what are the noise and how we can determine that your system is running in which location or in which noise limited region. So basically there are three types of noise. One is the detector noise. You can also call this detector noise as a dark noise, or sometimes we call as a thermal noise. Then another noise is a short noise, and third type of noise is called relative intensity noise. Sometimes we call it as a Bose-Einstein noise. So one thing to notice is that the dark noise, so if we look at the white line, this is overall line and this is the slope. So the detector noise that we see here doesn't change about the intensity. X-axis is the intensity, log intensity. Y-axis is the noise power. So the dark noise, if we look at the region 1, the dark noise portion, we see that it's not changing over time. And if we look at the short noise, what we see that as the intensity of the light increase, similarly the noise power also increase, and it's linear. If we look at the slope is 1. That means we can increase the light source power, and the noise power will increase linearly. It will not increase, it will increase linearly. But in case of green noise, what you see that if we increase the intensity level, we see that noise will be up pretty quickly, because here slope is 2. So if we increase here 1 unit in X direction, we will see the increase of noise in Y direction 2 times. If here 1, here will be 2 times, because slope is double. Here the slope, if we calculate slope is double. So as we cannot do anything about the dark noise, it will be constant at all the intensity level. But if we can run our setup in short noise limited region, then it's good, because then our signal to noise will be, we can increase the signal to noise ratio, and the phase noise or whatever noise we'll find in our setup will be low. We'll explain everything over the next few slides. So first I will talk about the short noise. Why short noise is coming? As I mentioned, that light is actually light, you can consider light as a photon. Einstein find that light is a photon, and there is another wave type light too. So let's focus on the light as a photon. So we are sending the photon, and this is photodetector. In our case, it is charge coupled device. So what the photodetector do is it converts the photon into electrons. It will generate the current, and from the current we can do some conversion and generate the image. So if we are sending, say, lots of photon, then there will be a fluctuation of the photon. It will not be always same. There will be a fluctuation. You can see this curve with this. There is a fluctuation. This fluctuation amount is a short noise. Usually the short noise current is equal to square root of 2 into Q. Q is the charge, I is the current, and the bandwidth. So say for example we are sending the stream of photons towards the camera, and over time this is a del t is some amount of time. Say for example del t equal to 1 second. So now in each time we see that there is a different number of photon we are sending to the camera. Here is n equal to 7 number of photon, n equal to 4, so different time, different photon we are sending. Now the noise will be the proportional of, say if we do the average of all the photon, it is 4, and the noise is that how much fluctuation we are getting from the mean power here. So if the fluctuation is more, then noise will be high. It depends on the percentage of fluctuation. We can calculate this kind of noise using the Poisson distribution. And if you do the analysis in the Poisson distribution, you will see that in the low light means if you send the less number of photons to the charge coupled device, you will see lot of fluctuation. The percentage of fluctuation is high from the mean. But if you send the more amount of light, then percentage of fluctuation is low. Number of total fluctuation will be high, but percentage of fluctuation from the mean will be low if we send high amount of photon or the higher intensity of the light. So, and another special characteristics of short noise is that it's white noise. That means is that this noise will be similar at all frequencies. It doesn't depend on frequencies. In x-axis here is the frequency, and the y-axis is the noise, and we see that noise doesn't change over time. It remains same. Now, how can we calculate that your system is short noise limited or other reason? Say if we collect the intensity over time for different time period, and if we calculate the standard deviation of the intensity for different time period, and if we plot that, we see the distribution of the standard deviation. That means the fluctuation of the light over different intensity. Now, if we plot this line and do the feeding, then we will see that slope of, if we find that slope equal to 1, then we can call that our system is running in short noise limited area. Because if we recall that in the short noise limited region, we have seen that the slope is 1. So, and also if we have calculated and found that slope is 1 for our spectral domain OCT setup. So we are running in the region of short noise limited. So now let's focus on other two noise. So dark noise. So dark noise will be always present in your data, because dark noise is even in the absence of light, thermally generated electrons will be collected in CCD and will contribute overall signal measurement. That means even though if you don't send any light from the laser, if you take the data from your camera, you will see some fluctuation. That means camera or the CCD will collect some photon. This photon will be generated mainly for the thermal fluctuation. So, and also if temperature increase, if we increase the temperature, then the CCD will increase higher number of photon. Say we are not sending laser light to the camera, but say everything is off, and we are varying the temperature of the room where there is a CCD camera. We will see that it's collecting number of photons, different number of photons, and the collection of number of photons will increase if we increase the temperature. So we cannot do anything about the dark noise except reducing the temperature of the room where we will set up our spectral domain OCT. So, and if you look at the graph, that in the region 1, we see that for all intensity, this value will be same. The value of the dark noise will be same. So as long as you are limiting the temperature, you are assuming the temperature is constant of the room. If you fluctuate the temperature, then the dark noise will change, and the dark noise is low when temperature is low. It's temperature dependent. There is another type of noise called relative intensity noise. It's mainly due to the instability of the laser. If laser fluctuate, this noise will be high, and this is not a good noise. We don't want to run our laser on the relative intensity noise area, because in this area, if we increase the intensity, so this is intensity, this is noise. If we increase the intensity, the slope of this graph is 2. That means if we increase the intensity a little bit, say 2, then the noise will be increased by 4. The slope of this graph is 2. Tan theta equal to value. So we always want to run our setup in short noise limited region, and we can check by taking the data. Thank you very much.